Today we're going to start talking about two-column proofs. I know this is a strange thing to start on a day when I'm not here, but we can't really afford to miss a day, so I'm going to have you go ahead and get started, and then I'll give you any other help that you need when you get back. The good news is you're starting with something that you all know very well and probably miss, algebra. So when you get your two-column proof set up, it's going to look like this. Actually, let me back up for just a second. The first part of your packet has some properties that you've probably known for a long time, but maybe haven't thought about putting them into words in exactly this way. So these are some tools that you're going to use as you write the steps of your proof. So you have the addition property of equality. If A equals B, then A plus C equals B plus C. So basically in algebra what that allows you to do is add the same thing to each side of an equation and maintain that each side of the equation are equal. The same thing with subtraction, multiplication, and division property. Those are the properties you've used all along to be able to add, subtract, multiply, or divide each side of the equation by the same number. Reflexive property of equality just means that the same number equals the same number, that 2 equals 2. It sounds kind of silly, but when you get to the end of an algebraic equation, you know that when you put your answer back in for the check, you get 6 equals 6, or 2 equals 2, or 10 equals 10, and that tells you you've done your equation right. Again, you've been using this all along, you might just not have called it that. Another one that's very similar is symmetric. If A equals B, then B equals A. You have the transitive property of equality. If A equals B and B equals C, then A equals C. So this is something like if 1 plus 2 equals 3 and 0 plus 3 equals 3, then 1 plus 2 equals 0 plus 3. You also have the substitution property of equality, which basically allows you to substitute a number for a variable and vice versa. So let's go back to our two-column proof. So basically when you have a two-column proof, you're going to have a statement in the left-hand column and a reason in the right-hand column. And as you read in the article on proofs, most mathematicians wouldn't be caught dead doing a two-column proof formally in the real world when they publish a paper. So you can think of this like our outline. We'll eventually outgrow the two-column proof, but it's a really great place to get started. So when you start with your two-column proof, the first line of your proof is going to be what you were given to start with. So this is the equation, in this case, that we were given to start with. So we write that on the first side, and you can see that you're working along with me on this page of your packet. So I'm working that problem in your packet. Okay, and so the first reason that you're always going to give is given. Basically, you're saying that's what they gave me to start with. Okay, and then you start doing some legal moves. Okay, so you do some things that you are allowed to, actually I wrote this wrong, didn't I? You do some legal moves that allow you to isolate the variable. So one thing that I might do is subtract 3x from both sides. Okay, and then I end up with 12 equals 5x minus 18. So that was my second step, so that's why I write number 2. And the right-hand column is why I'm allowed to do that. I'm allowed to do that because of the subtraction property of equality. The third step, I'm going to add 18 to both sides. So I'm going to get 30 equals 5x. And why was I allowed to do that? The addition property of equality. Then I can conclude that x equals 6. How did I know that? Because I divided both sides by 5 by the division property of equality. And the last step is saying that x equals 6. We're basically just writing it the same way. And this might be a reason that you're not quite sure of. So you can go back over here to your packet and see if A equals B and B equals A. That is the symmetric property of equality. So I can say that by the symmetric property of equality. So there's my basic 2-column proof. I started with a given statement, and here's what I was asked to prove. You'll notice that the last line of my proof is exactly the prove line. Do you see how I got really close right here, but I still had to add one more line to make it look exactly like the prove line? So the left-hand column of your proof, just to recap, is your statement column. That's where you're actually doing the work. It's your progression of thoughts to get down to x equals 6. The reason column is why you're allowed to do that proof, or why you're allowed to do that step, I should say. Okay, now let's look through the rest of your packet. As I said, the first 2 pages are just some more examples and some notes. When you get to the second page, you have some geometry statements that you're allowed to use, or some geometry theorems, and you're allowed to use those in the reason column as you make different statements when you're proving things geometrically. So then here's another recap of the properties of equality that you got in the first part, and here are some algebra proofs to practice. And this will just get you warmed up because algebra is something that you're used to doing. So I'm going to have you work through these first just to get used to writing your statement and writing your reason, and think about in every single step, why am I allowed to do that? Why is that a legal move? The next page will start you on some geometry proofs. And so here are some properties of congruence that will be really helpful as you think through this. It also notes that you're allowed to use definitions, postulates, previously proved theorems, we don't have any of those yet, and algebraic properties. Algebraic properties just means that anything from the beginning of this packet, these things, can apply in geometry as well. Let me get you started with the first one. So this says the line segment XY is congruent to the line segment BC. Well, what it wants you to prove here is that XY, the length of XY, is equal to the length of BC. Well, this is just going to be a very simple one-step proof, because by definition, see, that's one of the things you're allowed to do, when 2 lines are congruent to each other, they have equal measure. So since these 2 lines are congruent to each other, they have equal measure. So basically you would write XY is congruent to BC, and that is given as your first step. And then the prove line is just simply the next step. Again, we're starting super easy here. XY equals BC because of the definition of congruence, which says that 2 lines that are congruent have equal measure. You'll see a very similar one down here. And then we get a little bit more complicated. But I bet you will be able to go back for each one of these and find one of the properties that's really useful in helping you get from your given line to your prove line. You'll work through some more of these, and they'll get gradually more complicated, but I don't want you to get frustrated with yourself. Just think about, what information do I have here that I know in the given, and what do I know from the diagram? Be careful. Remember, you can conclude position but not measure, and that should help you step from the given to the prove line. You'll work together on this, and I'll help you with whatever questions that you have when I get back. See you on Wednesday.